Hello and welcome to lab. This week we're going to start working on nomenclature in lab. Nomenclature is just the fancy word that's given to naming chemicals. So in this lab, what we're going to do is learn how you name chemicals. Nomenclature is arguably one of the most important concepts that you can learn in this course, because nomenclature is one of those things that it shows up over and over again. Right now it's being directly taught, and there'll be some stuff that's directly tested with regard to nomenclature, but what you'll find is when you get into chemical calculations and chemical reactions, nomenclature is indirectly tested. In other words, if you don't know your nomenclature, you might not be able to get a problem correct. I would argue one of the best pieces of advice you can give a student that is struggling in inorganic chemistry is to work on their nomenclature, because if you don't know your nomenclature, it can really throw you off when you get to other concepts that rely on nomenclature. So take nomenclature seriously and work hard on it in this lab, and it's really gonna pay off as you go through your chemistry career. In this series of talks and slides, I'm going to go through the different compound types and some of the naming that you're going to need to know to complete the lab and name compounds that you'll encounter in chemistry. So in this first video, I'm going to talk about the types of compounds and ions. We're gonna spend some time talking about the nomenclature of ions, because they're going to be brought up when we start naming these types of compounds. There are, broadly speaking, inorganic compounds and then organic compounds. Things like acids fall into that category. From these types of compounds, in this blue box, you have three types that you're going to have to learn how to name: ionic compounds, molecular compounds, which are also called covalent compounds, and then aqueous acids. So these three types, they all have a unique sort of nomenclature that you have to follow, and so we break them up into three different groups like this. And so we'll look at each one as we go. But first, let's talk about ions. When you have to name acids or ionic compounds, you're going to be dealing with ions, and so it's important to get some of the nomenclature for ions down. Ions are charged, right? They're charged particles that form when you either gain or lose electrons. If you lose electrons as an element, you form a positive ion called a cation. If you gain electrons, you become an anion. From both of those, cations and anions, you can further delineate them into monoatomic or polyatomic cations or anions. Monoatomic cations are generally going to be metals that lose electrons to become positively charged. When we name a monoatomic cation, cations, we're just going to use the parent name, the parent element name, followed by the word ion. So check it out. Sodium plus, it's clearly an ion because it has that positive charge. You're just going to name it as sodium ion because it has that positive charge. Aluminum, you're going to name as the aluminum ion. It's aluminum 3+, so it's a cation. You're just going to name it aluminum, which is the parent name, followed by ion, and you're good. Notice that these ions only consist of one mono element, right? One atom, so monoatomic. That's why we call them monoatomic, because there's only one atom involved with the ion. Monoatomic anions are going to be nonmetals, predominantly always nonmetals, because nonmetals are going to gain electrons to give you a negatively charged ion. With a monoatomic ion, you have to do a little something extra. You have to drop the name, the end of the name, on the parent compound or parent element, and you have to replace it with IDE. So monoatomic anions are named by dropping the last part of the element and adding this IDE. Take, for instance, bromide. To come up with the bromine ion, which is bromide, you're going to take bromine, you're going to drop that green part here, and you're going to replace it with IDE. You replace it with IDE, and you get bromide. So the Br1 minus anion is just bromide. And you don't have to say ion at the end. You just say bromide, and then you're done. If you look at oxygen, you're going to, when you form an ion, drop the YGEN, replace that with IDE, and you get oxide. For nitrogen, you're going to drop the OGEN when you're naming the anion, and you're going to get IDE. You replace that OGEN with IDE. For all the monoatomic anions, they're all going to end in "ide." They all end in "ide." Notice you're only dealing with one atom. That's where you get the monoatomic from. In terms of getting the charge on the ions, you can look to the periodic table. When you're looking at main group elements, which correspond to the elements in groups 1, 2, and then 3A through 8A, those are your main group elements. You can predict those charges just based on where they are in the periodic table. And it goes back to their valence electrons, how many they have. But the way to think about it is elements that are in group 1A, so hydrogen all the way to francium, those all form +1. Elements in group 2A all form +2. 3A, you've got a few that form +3. And then once you get into the nonmetals, 5A through 8A, you can have 3-, 2-, 1-, and then the halogens don't pick up any charge at all because they're noble gases. But some of the elements, again, specifically the ones that are in the main group, can be predicted, the charges can be predicted based on where they are. One thing that we're going to see is that some metals, typically the transition metals, so remember transition metals are all the guys in here. You got your transition elements. They just happen to all be metals. When you have elements that are in that part of the periodic table, they can have variable charges. Sometimes you'll hear this referred to as variably charged metals or variable ionic charged metals. And what we see is they can have different charge states. And one example of that is iron. Iron, Fe, can be either 2+ or it can be 3+. Because, if you named this cation conventionally, based on just the nomenclature we've talked about, you would call both these iron ion. You have to use a Roman numeral to specify which iron ion you're talking about. If you have Fe2+, you use the Roman numeral 2. If you have Fe3+, you use the Roman numeral 3. So real important, when you're talking about variably charged metals, that is the ones that can have different charges, you're going to include the Roman numeral in your naming. And here are some that you will commonly encounter. So they're indicated in green, like titanium, gold, mercury, lead. Those will all have variable charges to them. Notice these 3 in yellow. This is silver, cadmium, and zinc. Those actually don't have variable charges. So they're transition elements, but they have predicted charges. You can't predict them based on where they are in the periodic table. It just turns out that they have these predicted charges. Really important, you can't predict the charge on variably charged metals or variable oxidation state metals. You could think of oxidation state as kind of just being charged right now. You can't predict the charge on these metals by looking at the periodic table. It's really important to know. You're gonna have to figure it out based on what else they're bonded to, which we haven't talked about yet. But for now, just know you can't predict them based on where they are. All right, so let's summarize the variable oxidation state metals, which are just your variably charged metals. You can't predict them based on the periodic table. They can assume multiple charges. If what that means is they can, be +2 or +4. Non-Voss metals, variably charged metals, are things like potassium that you can get from the periodic table. Variably charged metals are like lead. See, lead can be 2+ or 4+. And then importantly, the variably charged metals, you have to indicate their charge with that Roman numeral, right? So you got lead 2 ion. That Roman numeral 2 indicates that you're dealing with a +2 ion. And then for lead 4+, you have to have that Roman numeral 4 in order to indicate which ion you're talking about. So summarizing the monoatomic ions, you have cations, right? First and foremost, that was the first one we talked about. With cations, you're just going to name the metal followed by the word ion. So for instance, zinc is going to be zinc ion when it's zinc 2+. Cesium, Cs, is going to become cesium ion when it's cesium+. The anions, on the other hand, you're going to do a little change to, right? You're going to drop the ending and you're going to add IDE. So for arsenic, you're going to drop the ic and you're going to add ide. For iodine, you're going to drop the Ne and you're going to replace it with ide. Or you drop the INE and you replace it with ide. And then those Voss metals, those variably charged metals, have that Roman numeral when you're talking about them. Let's quickly talk about polyatomic ions. Polyatomic ions are going to be charged particles that have more than one atom involved. So there'll be multiple atoms. Overall, they will have a positive or a negative charge. What we're going to see is that most of these ions that are polyatomic are going to be negative, with 3 exceptions. You can have some that are going to be positively charged, and those include things like ammonium, hydronium, and then mercury. In the common ions handout, just had it up. There we go. In this common ions handout that I posted, you can see that there's common ions that are always +1. They include like ammonium ion. That ammonium ion, notice how it's a nitrogen and 4 hydrogens. That's a polyatomic ion. If you go down to things like acetate, nitrate, nitrite, those are all also polyatomic ions because they have more than one atom. So if it's charged and it has more than one atom, that's when you're dealing with polyatomic ions. All right, so if you're gonna practice these, rubidium is a metal, so you'd name it rubidium ion. Oxygen, the ion that would form with that is oxide. Cadmium would be cadmium ion, because cadmium is a metal, forms a positive charge. Nitrogen is a nonmetal, gains electrons to become nitride. Selenium is also a nonmetal. It's going to gain electrons to become selenide. Phosphorus becomes phosphide. Fluorine becomes fluoride, and then lithium becomes the lithium ion because it's positive. If you were gonna, go from the chemical formula to the name, something like tin 2 ion would look like Sn2+. S2- is sulfide. Iron 3+ is iron 3. The iron 3 ion. You would need to know iron is one of those variably charged metals. That's why you're adding that Roman numeral 3. Copper. Copper can be +1 or +2, so the copper 1 ion, is just 1+. Magnesium 2+ is just the magnesium ion. Magnesium is not one of those metals that has variable charges, so you just can say magnesium ion. Bromide you write as Br-. Manganese 4+ becomes manganese 4 ion. Manganese is one of those that can have multiple charges. And then the silver ion, Ag1+, is just silver ion, because silver again can only have that one charge. All right, so let's summarize the three types of compounds and what you're gonna encounter with each before we jump into the nitty-gritty of naming. For ionic compounds, they're always going to contain a cation, and they're always going to contain some kind of anion. And overall, they are going to be neutral. They're not going to be charged. Ionic compounds include things like sodium chloride, ammonium sulfite, and then aluminum nitrate. Importantly, ionic compounds have a metal. They have a metal in them. That's how you're going to know they're ionic, because they have a metal and then they're going to have a nonmetal. So like non-ionic compounds are things like CO2, HPO4, and then PCl3. Those are non-ionic because they don't have metals in them. We're going to talk more about ionic compounds in lecture, but for nomenclature you have to know this. And right now the level that you need to know to identify an ionic compound is that they have a metal bonded to a nonmetal. The next one is molecular or covalent compounds. These are only going to contain nonmetals, right? Remember in lecture we talked about how you identify metals from nonmetals in the periodic table? If you have atoms that are on the right side of the periodic table that are nonmetals and they're bonded together, you're dealing with molecular or covalent compounds. So for instance, P2Br5, glucose, which is C6H12O6, and NH3, those are all molecular. They're molecular because they don't have a metal involved. Non-molecular compounds are going to have a metal and nonmetals. So things like aluminum trichloride, aluminum's a metal, chlorine's a not, so it's non-molecular. Ions are not considered molecular compounds or covalent compounds because they're charged. So one thing we notice with all of these types of compounds, molecular is not an exception, is that overall the charge is neutral. And so ions are not going to be considered molecules. They're not molecular compounds or covalent compounds. And then the last thing is aqueous acids. So for aqueous acids, you're going to see that they have to begin, the chemical formulas are going to begin with a hydrogen. There's always going to be a hydrogen out in front. The name or the chemical formula is going to end with AQ. You're always going to end with AQ. And then overall, they are going to be neutral. So all of the compounds overall are neutral, right? So aqueous acids, you have an H out front in this example. That's what we mean by H being out front. It's in front of the chemical formula. It ends in aqueous. Aqueous means water. These acids are going to be in water, so you always see AQ. HC2H3O2 has the H out front. It also has the aqueous. That's how we know it's an acid. HF has the H out front, followed by aqueous, so we know it's an aqueous. Non-acids are things like lithium bromide. It has the AQ, but no H out front. HCl has an H out front, but notice there's no AQ. NH3 has the aqueous, but no H out front, so it's not an acid. All right, we're going to go ahead and work on naming these individual compounds now. So sit tight for that.